Hello, dear students. This is the podcast of 7th lecture. So, in this lecture, we will discuss outer measure generated by a measure. In the previous lecture, we have constructed an outer measure generated by a set function mu, where this mu is a set function from f to 0 to infinity with the property that mu of phi is equal to 0. This phi is a member of f. So in the previous lecture we have seen that the function, the outer measure generated by this function mu, which is a set function from f to 0 to infinity with the property that mu of empty set is equal to 0, and we have seen that outer measure is defined by mu star of a is equal to infimum of summation n runs from 1 to infinity mu of an, with these an's they are the members of f, where f is a collection of subsets of x with the empty set the member of f, and this a is a subset of union a and also 1 to infinity. Now here in this lecture we will take the special collection of subsets of x. Instead of f we will take a summary, and instead of any set function we will take a measure, and we will see certain properties of this outer measure generated by a measure. And in these previous lectures, we have seen that this mu star of a is less or equal to mu of a for whenever a belongs to f. And here we see that this mu star of a is exactly equal to mu of a if a is a member of summary. If a is the member of summary. So in other words, here we will see that this mu star is actually an extension of a measure. Okay, so we recall that in this lecture x mu is a fixed measure space. So let me write here throughout this section. Throughout this section, x mu is a fixed measure space. Now we recall that the outer measure generated by mu, that the outer measure generated by mu is defined as mu star of a is equal to infimum of summation n runs from 1 to infinity mu of an, where these an's here they are the members of summary, and a is subset of union a and n runs from 1 to infinity. So that's already defined in the previous lectures. We have first term in this section. In that term we'll see that this mu star is an extension of mu. So that means when we restricted this mu star to this collection, it will coincide with mu. It's an extension of mu. So that's this theorem. Let xs mu be a measure space. Let xs mu be a measure space. Then mu star, it's the outer measure generated by mu. The outer measure generated by mu is an extension of mu. Is an extension of mu. Is an extension of mu. So by extension, we mean that when we restrict our mu star to this collection S, it will coincide with mu. That is, mu star of A is equal to mu of A for all A belongs to this collection S of semi-rings. So let's prove this theorem. So as already proved in the previous lectures, mu star of A is always less or equal to mu of A for all A belongs to S. It's already proved. So I will write here already proved in previous lectures. Mu star of A is always less or equal to mu of A for all A belongs to S. Now we prove the reverse inequality. So for this reverse inequality, we choose let A be any member of S. Any member of S. So let's choose let's take any sequence and let A and B any sequence in S such that A is subset of union A and n runs from 1 to infinity. So such that this A is subset of union n runs from 1 to infinity A n. Then we can see that by sigma sub additivity of mu, we have mu of A. First, it is less or equal to mu of this. We cannot say it's less or equal, but this it's less or equal to summation n runs from 1 to infinity mu of A. It's by sigma sub additivity. Okay. So now here let's apply infimum on this collection An from S covering A. Let's take infimum over all those collections having this property. So this will give mu of A will be less or equal to infimum of summation n runs from 1 to infinity mu of A such that An belongs to S and A is subset of union An. Now, by definition of mu star, this infimum it's equal to mu star. So this implies mu of A is less or equal to mu star of A. So thus mu of A is equal to mu star of A for every member of the summary S. So that means mu star is an extension of mu. Mu star is an extension of mu. So now in future by by measurable set A, we shall mean it is measurable. We shall mean it's measurable with respect to mu star. The outer measure, the outer measure generated by mu. So in future, whenever we have a measurable set, it means that it's measurable with respect to the outer measure mu star generated by this mu, generated by measure mu. It's measure here, generated by measure mu. Now we have some interesting properties of those measurable sets. Now we have some interesting properties of measurable sets. Some of them are listed in the following terms. Some of them are listed in the following. So for those class of measurable sets, we have certain interesting properties, and some of them we have in this theorem that we are now going to discuss. And the theorem is it's a very important term for those class of measurable sets. That excess mu be a major space, and let mu star be the outer measure, be the outer measure generated by mu. Then for a subset E of X, the following are equivalent. The following are equivalent. First, A is measurable, and second is mu of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement. For every member of submeaning S, for all A belongs to S with its outer measure finite. We can write here mu because the mu star is same as mu on S. So let me write here mu. Mu of A is finite. Mu of A is finite. And third property is mu of A. Sorry, it's here equal to. And next is greater or equal to mu of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every member A of S with its outer measure finite. And fourth property, it is mu of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every subset A of X. So that theorem is very important because for measurability we must need this inequality. mu of A must be greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every subset of X. Then the set E is measurable. But this theorem states that if this inequality holds only for those subsets of X which are the members of sum ring, not all the subsets of X, then still the set E is measurable. So that's very interesting property of the class of measurable sets which are measurable with respect to the measure mu star generated by the measure mu. So otherwise we have to check all the subsets. For each subset we have to check this inequality. But for but for those measurable sets which are measurable with respect to mu star, we have to check this inequality only for those subsets of X which are the members of semi-ring. So that's why this theorem is very important. So let's prove this theorem. Prove. First implies second is trivial because if E is measurable, then mu of A is equal to mu star of A intersection E plus mu star of A intersection E complement for every subset A of X. In particular, it's true for those subsets of X which are the members of S. So that means this equality trivially holds. And second implies third is also trivial because whenever we have mu of A is equal to mu star of A intersection E plus mu star of A intersection E complement for every member of S with its measure finite, then this also holds. Mu of A must be greater or equal because it's equal to. So second implies third. It means mu of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every member of S with its measure finite. So now third implies fourth is important because third is valid only for the members of semi-ring, but we have to show that it should hold for every subset of X. So this is important. So first implies second implies third or trivial. So now we prove third implies fourth. Third implies fourth. So assume third holds. Assume third holds. That is, mu of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every member of semi-ring S with its measure finite. We prove 4. That is, we prove this mu of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every subset of X. So let's prove this. Third implies 4. Third implies 4. Okay. So if first case, if in case mu star of A is infinity, then this trivially holds. Infinity is greater or equal to this number. Then we are done. So we assume that mu star of A is finite. But what's mu star? It's actually the infimum of certain class of sums. So it's infimum of that set. Now let's apply the property of infimum. Okay. So let epsilon be any positive number. We can choose as sequence. an in S such that such that summation n runs from 1 to infinity, mu of a n will be less than mu star of a plus epsilon. So if I add epsilon to this increment, it will be greater than some member of the set. So that member is this. And this is finite because mu star of a is finite. So mu star of a plus epsilon is also finite. So that means this series is finite. Therefore, mu of each measure is finite. Mu of each an is finite. Mu of each n is finite. So measure of each. So this implies mu of an is finite for all n greater or equal to 1. Greater or equal to 1. Now it's given that third holds. So by third, it's mu of an is greater or equal to mu star of an intersection E plus mu star of an intersection E complement. This inequality holds for the members of submeasuring S having measure finite. And here an is a member of S and its measure is finite. This is true for all n greater or equal to 1. So now we check this. Now we need to show that mu star of A should be greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every subset A of X. Now let A be any subset of X. Then we check this mu star of A intersection E plus mu star of A intersection E complement. We show that this is less or equal to mu of A, mu star of A. And this A, it's a subset of union An. A is subset of union An, and mu star is monotone, so it's less or equal to mu star of union n runs from 1 to infinity An intersection E plus mu star of union n runs from 1 to infinity An intersection E complement by as mu star is monotone, and A is subset of union n runs from 1 to infinity An. Now let's apply the sub-additive, sigma sub-additive property of mu star, because the mu star is outer measure is sigma sub-additive, so it will be less or equal to summation n runs from 1 to infinity mu star of An intersection E plus summation n runs from 1 to infinity mu star of An intersection E complement, as mu star is sigma sub-additive. So this it's less or equal to this. I will not erase this inequality because to use this inequality here. So let me erase this part. So here we have this mu star of A intersection E plus mu star of A intersection E complement is less or equal to this sum. So since it's a finite sum, so this will be less or equal to summation n runs from 1 to infinity mu star of An intersection E plus mu star of An intersection E complement. So here, this is less or equal to that. Now look at here. mu star of A n intersection E plus mu star of A n intersection E complement is less or equal to mu star of E. So it's less or equal to this one. It's summation n runs from 1 to infinity. This sum is less or equal to mu of A n. It's less or equal to mu of A n. And as from the property of the infimum, this is less than mu star of A plus epsilon for all epsilon positive. And now letting epsilon approaching to 0, we get mu star of A intersection E plus mu star of A intersection E complement is less or equal to mu star of E. So that proves fourth. Mu star of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every subset A of X. So first 1 implies 2, 2 implies 3, they are trivial, and this is third implies 4. Now we show fourth implies 1, so that proves all the 4 statements are equivalent. Now we prove fourth implies 1. Assume fourth holds. Assume fourth holds, that is mu star of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every subset A of X. We show first holds. That means that is E is measurable. E is measurable. That is E is measurable means mu star of A is equal to mu star of A intersection E plus mu star of A intersection E complement. So it's given and you have to prove this equality. So since this inequality always holds, since mu star of A is always less or equal to mu star of A intersection E plus mu star of A intersection E complement for every subset A of X. This is always true. So this is given. Fourth is given. It's true for each subset A of X, and this is already known. Mu star of A is always less or equal to this. So combining these two inequality, we get combine these two inequalities. So we get mu star of A is equal to mu star of A intersection E plus mu star of A intersection E complement for every subset A of X. So hence E is measurable. Hence E is. This completes the proof of the theorem. So definition, now in future we say a subset E of a major space of a major space excess mu is measurable if it is measurable with respect to mu star, the outer measure generated by a measure with respect to mu star. Okay. So we say subset E of set major space, fixed major space. It's any subset of X, and we say it's measurable if it's measurable with respect to mu star, while mu star is an outer measure generated by the measure mu. So let's have a following theorem. Actually we had to check which subsets of which members of Px are measurable. If E is a member of Px, is it measurable or not? So in general, all the subsets of X are not measurable, or all the members of Px are not measurable. But here this submeaning, it's a subset of power set of X because it's a certain class of subsets of X. And now in the next theorem we'll see that every member of submeaning is measurable. Every member of submeaning is measurable. So that's a very important property because it has a number of applications. So let's first do this theorem. Every member of a submeaning is measurable. Let X as mu be a measured space. Then every member of S is measurable. Measurable means it's measurable with respect to the measure mu star, where mu star is an outer measure generated by mu. So that means we need to show that this S is subset of lambda, where lambda is a class of measurable sets. Proof. So let E be any subset. Let E be any member of submeaning. We show that E is measurable, and by previous theorem it is sufficient to show that by previous theorem it is sufficient to show that mu of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement for every member of S only. It's already proved. And only those members of S having measure finite, with mu of A is finite. So by previous theorem it is sufficient to show that mu of A is greater or equal to mu star of A intersection E plus mu star of A intersection E complement. This should hold for every subset A of S with its measure finite.